us about the theorem of Berger.
The what?
Berger.
Berger's holonomial theorem?
Yeah. What?
The holonomial theorem by Berger, the classification of holonomial groups.
Which type of techniques are involved in this type of theory?
Okay, there's several proofs of this now. The original proof was by a tedious case-by-case classification, and the main restriction was that the Bianchi identity gives you additional information about properties of the holonomy group and its representation. So then you have to use representation theory also. Say, what can you say about the weights and the roots, and to try to determine the representation that way. And somehow Bianchi identity is the main tool, but then it becomes a tedious case-by-case classification. So it's something that's not fun to go through. Now there are more conceptual proofs. There's one by Simons, which is a purely algebraic one, but conceptually it doesn't use classification at all. So he really proves this version that either it's transit on the sphere or it's symmetry space. He proves that directly conceptually. And it's a strange proof. I actually went through that in class once. It takes a while, probably too long for it to be worth it. It's one of these proofs where you can follow every step, but at the end you don't know, you don't really understand why it worked or how it worked, right? So usually, if you understand a proof well enough, then you say, oh, okay, this is certainly very natural. This and this is a natural thing to do. In that case, Simon's proof, I never understood why it's natural. And the more recent proofs, which I haven't read yet, due to Carlos Olmos. He also has a more geometric proof. I would have to take a look at that to see how that works. I've never done that. But that may be less, I don't know, this may be not as interesting in that context. What may be interesting is to talk about the special geometries that are associated with the ones where it's not a symmetry space. So in each case one can say a lot. That's certainly, as far as applications are concerned, that's very useful. Whereas a proof of the holonomial theorem is not that useful as far as applications are concerned. Okay. But special properties, that's quite interesting. So at the end of the lecture today, we should decide what we want to do the rest of the semester. And I'll give maybe a 10-minute presentation on some of the topics we can work on. But we have to decide. Okay, a little bit more duality. And a little bit of a classification with symmetry spaces. So let's see, what should I recall? A couple of things. So, as usual, symmetric pair. And then a corresponding Cartan decomposition into plus and minus one eigenspaces with respect to d sigma. And then we had several definitions. So first let me remind you that it's called irreducible if at k acts irreducibly on P. That's the isotope presentation. There is an equivalent way of saying that for all practical purposes, namely a reminder that if pi 1 of G mod k is 0, this implies that k is connected. So since we always assume G is connected, so if G is connected, the space simply connected, K is connected. This was a consequence of a long homotopy sequence. And so then irreducible is equivalent in this case to saying that little at K acts irreducibly on P. So I can reduce it to a Lie algebra, just a Lie algebra statement. That was irreducible. And then remember, a general consequence was that if this pair is almost effective, like we usually assume, this implies that the killing form restricted to K was negative definite. So B was the killing form of the whole Lie algebra G. So that was an important property. And then we defined the type. So we said compact type was B restricted to P positive, non-compact type P restricted to P negative. Sorry, other way around. compact means negative. This means positive. Right, in this case here, the killing form of G is negative definite on the whole thing, and that's a compact Lie group, so that makes more sense. And the Euclidean type, if it's type 0. And then I won't write it all down anymore. We had the theorem say if you have a simple connected symmetric space, it's a product of things that have compact type, non-compact type, and Euclidean type. If it's simple connected type, if it's simple connected, Euclidean type is just Rn, so we split it off. It's not interesting. So we can assume things are compact and non-compact type. The next thing was we defined a duality between non-compact and compact type, which went as follows. We take a symmetric pair G mod K. G is my Cartan decomposition. And then I look at G prime is equal to K plus IP inside the classification of G tensor C. Then we observed G prime is a subalgebra, a real subalgebra. And of course, K is contained in G prime. And then G prime comma K prime gave me another symmetric pair, which we call the dual order symmetric pair G comma K. If M is simply connected, then this is uniquely determined. Then I can choose G prime to be my simply connected Lie group, whose Lie algebra is G prime, K prime the corresponding subgroup. Then this space is simply connected. Then I get a one-to-one correspondence. So one-to-one between GK compact type, simply connected with G comma K non-compact type. And simply connected. Otherwise, it's only up to coverings, but that's less interesting. And remember that this goes from compact to non-compact. It's very easy, because in P I multiply by I. That means in the killing form, I multiply by I twice. It changes the sign of the killing form on P, so it makes negative to positive, just because I multiply by I here. So that's my duality between compact and non-compact type. We saw some examples last time. I want to do one more example, which is kind of interesting, which was a symmetric pair. So if K is compact, then K cross K, comma diagonal K was a symmetric pair. And the involution was just switching the two factors whose fixed point set is just the diagonal invariance. This was a symmetric pair. Of course, a compact type, since the Lie group is compact, killing form must be negative definite. So this is our compact type. Another question is, what is the dual of that? It must be a non-compact symmetric space, right? Non-compact type meant both that the manifold is non-compact, the Lie group is non-compact. By the way, I think another thing that we observed was the killing form is always not for compact and non-compact type. The killing form is not degenerate, but it's negative here and positive here. So G is semi-simple. So we're already in the world of semi-simple Lie algebras, which makes things much easier. They're classified. Okay, so it's just another reminder. So what's the dual? What are we supposed to do? Let me write it down like this. And this is a little tricky. Write it down in the right order. Here. Okay, so let's do it in the Lie algebra level, right? So G is K plus K. And we have diagonal K embedded in there as our stabilizer. Maybe I shouldn't call it K since we have a K here already. Let's give it a different name. Too many Ks. Let's call the Lie group L here. So then G is L plus L, and K is diagonal L. So set of all x comma x. There's x and L. So that's a plus 1 eigenspace of the evolution. It switches them. P has to be the minus 1 eigenspace. So that's a set of all x comma minus x, where x lies in L. But now the evolution that switches them takes that vector to its negative. So here's my plus 1 eigenspace, my minus 1 eigenspace with respect to this evolution there. So I should think here as L plus L. Evolution switches the two things. So that's my Cartan decomposition of the Lie algebra G. And now we're supposed to take G prime is K plus IP inside G tensor C. Well, what is G tensor G? G is the direct sum of two things, so it's L tensor C. So let's call it LC, direct sum LC. So this sits inside LG plus LC. So K just diagonally here, and P. So the P inside here is then set of all IX minus IX, X and L. But I want to describe this in a different fashion so I can recognize what G prime is. Maybe I should write down the claim. Claim G prime, comma, our new K, right? Stabilizes is the same, is equal to LCR comma L. Of course, notice here that K is isomorphic to L, right? So if I write K there, or L, it's the same thing as long as I think of this as embedding. So what does this say? It says that, so what does this pair mean here? So I take L as my compact Lie algebra. I complexify, and then I regard it as a real Lie algebra. Okay. Inside that sits L as a real Lie algebra. And what's involution here? Sigma prime of something A is just A bar. So then inside here, so this is a real Lie algebra isomorphism. Right? It's not compass linear, but if I forget about the compass structure, it does become linear of the real. So it's a Lie algebra isomorphism. It's clear in involution. And the fixed point set is precisely L, the real points. So that makes this into a symmetric pair. And the claim is that's what the dual is. So what is if I look at this involution here, what is K and P? So K is equal to L, right, inside LC. And what's P, what should we call it? P star maybe? Sorry, this is I times P, right? No, let's call it P prime. So instead of all A in LC, where A bar is minus A. So this would be P prime. That doesn't look like I times P yet. Doesn't look like it yet. So I have to. I'm going to define an isomorphism that takes one pair to the other pair. So I want to define something which takes G prime comma IP into G comma P prime. That's maybe right. So okay. So what automorphism do I do? Okay, so for this I take an automorphism A from LC plus LC into itself, which takes x1 plus iy1, x2 plus iy2. Right, everything in here is a real plus I times something real. Takes it into x1 plus iy1, x2 minus iy2. So I just change the sign on the second component here. And so I claim this is a real automorphism. Because how do I take Lie brackets in the complexification? Just by taking Lie brackets of the real part, the imaginary part. So if I take Lie brackets here, real and imaginary, that fits in here also. It's also clear in involution, but if I do it twice, I multiply a minus sign twice in the second component, I come back to itself. But I don't think that's important. But what is A? What is A of IP? So IP was IX comma minus IX. So that's sits here, takes it to IX minus IX. Where X lies in L. So, and notice that's what P prime looks like. Right? So now this is precisely those where A bar is minus A. So that's P prime. So it's the same symmetric pair up to some automorphism. The automorphism is a little bit tricky. It's just kind of like we did it last time for the Grassmannian. Right? The dual pair wasn't what you expected on the nose, but we had to apply an automorphism to take one to the other. Okay. Pardon?
Wouldn't be the imaginary diagonal vectors ix, but minus. We need to change the.
Ah, yes. Hey, so IP was this. Ah, okay, it's plus here. Ah, of course I want A, but you minus A. So that's certainly true here, right? X is real. Ix is imaginary, so A bar is minus A. So that's still P prime. You're right. So that's a dual of a compact Lie group. Is this kind of non-compact pair, which I think of this as a Lie group. So if I look at L cross L, comma diagonal L, the dual to that would be LC, comma L. Right? Complexify your Lie algebra. Forget about the complex structure. Look at it as real. As a Lie group, that's what this looks like. That's non-compact now as a real Lie group. Inside L, here's a compact one. And that's the dual. Okay, so this much about duality, maybe. Yes? To P prime? Okay. One more result. before I do, say, an example of how one can easily classify symmetric spaces, is the following. That's kind of interesting. So again, take a symmetric pair, G, K, assume it's irreducible. And then it says that if G is not simple, then the symmetric pair is of the type we discussed over there. With K compact simple. So that's the only symmetric pair where indeed the Lie group G is not simple. Corollary, for example, if G, K is of non-compact type plus irreducible, this implies that G is simple. Because this here, the group G is compact, because K is compact. Particularly what it says that if I want to classify symmetric spaces, of course, on the one end, I have to classify compact simple Lie groups, which is something that's in the second chapter if you haven't done, but that's well understood. And then after that, one can assume the group is simple and classify symmetric spaces where G is simple. And I'll give you an example of how that is doable. Okay, let's prove this. That's certainly an important result. Okay, so let's take our symmetric pair. So G, the Lie attribute G, is semi-simple. So of course I should say irreducible symmetric pair, not of Euclidean type. Of course, then it's not true. Right, for Euclidean space, the group G was rotation, semi-direct product of the translations, so it's non-compact, but it's not of this type. So it's false for Euclidean type. And of course, we always exclude that. That's not interesting. And then it's supposed to be true. So now G is semi-simple. So this implies that G is a direct sum of ideals. So where Li are simple ideals. So the ideals, the direct sum of ideals, and each ideal is a simple Lie algebra. And this decomposition is unique up to order. So it's something we proved when we talked about semi-simple Lie algebras. In Pop and Popper, semi-simple Lie algebras. Now I have my automorphism, sigma, that defines my symmetric pair. So maybe I should add it here. It's always implicit. And of course, it takes G to G, takes an ideal to an ideal. So all it can do is you can only permute the ideals, because it's unique up to order. So sigma of an Li must be another ideal, so it must be one of the others. So sigma is automorphism. This implies that it permutes the ideals Li. Because there are now two possibilities. It can fix some of them, some it can preserve, and others it can take somewhere else. But since it's evolution, it would have to switch the two. Right? Either it switches to or it preserves it. So let's collect one type in the other type. So let's say you write G as, what should I call it? Maybe KL M M1 plus MR, where either mi is equal to sum Lj, and sigma mi is contained in mi. So I collect those ideals that are preserved by sigma, or mi is equal to Lr plus Ls, and sigma of Lr is equal to Ls. And of course, then sigma of Ls is equal to Lr. Particular preserves mi also. So in this decomposition, sigma preserves each factor, and each factor is either an Li preserved by sigma or switches to two of the Li's. So then sigma restricted to mi is also an involution, and therefore that means that mi splits also is equal to, shall I call it, ki plus pi. Plus minus 1 eigenspace decomposition. Of the mi's. Sigma and mi is another involution, have plus and minus 1 eigenspaces. Of course, there are also plus and minus 1 eigenspaces of sigma on the Holy algebra. So ki is contained in K, it's a plus 1 eigenspace, and Pi is contained in P, it's a minus 1 eigenspace. So it means that K splits up. How many do we have? R. And P splits up. And, okay. And I claim if I look at, say, if I define G, oh, that's already defined. And mi was pi plus ki plus pi. But this means that if I look at the action of, say, say the ith component, and restricted to the jth component, this must be 0 if I is distinct from j. Right, so these were all ideals. So I take Lie brackets of 1 with another one, I get 0, since they're ideals. Ki and pi all sit in one of these ideals. If I take mixed Lie brackets of some of these and some of the rest, I get 0. But at k is supposed to act irreducibly on p. So since at k on p is reducible, this implies that r is equal to 1. There can be only one of them in this decomposition. What was r? R was a number of factors mi, and remember mi is either one Lj or two of them. This implies that either G is equal to Li, so L1 say, and is simple, and that's one possibility in the theorem, or G is equal to L1 direct sum L2, and sigma of L1 is equal to L2. So that means I can think of sigma as an isomorphism between L1 and L2. So I claim this therefore is an isomorphic to L1 direct sum L1, just using the identity on the first one and sigma on the second one. And of course, then what's the fixed point set of sigma? Since I identify it here, this is simply diagonal L1. So sigma just switches it, it takes AB to BA. Since I identify the two. And that was our example of a compact, of a symmetric pair like this here. K cross K, comma K. So L1 is our K over here, and K is simple, because the Li's are simple over there, and that's it. So I reduce the whole story to simple Lie algebras. let me make some comments about classification now. There's a division into type that's historically was introduced by Cartan and is still used today. Type 1, 2, 3, 4. You have to remember which type. It's not so important. Type 1. Is K cross K, comma K, K compact simple. So here of pairs G comma K, irreducible symmetric pairs. To type 1, I have a dual. So these are always paired up by duality. And the dual is called type 3 for some reason, historical reason. And the dual was something of the type, how should I write it? Type KC comma K. Another way to describe this, or a pair G comma K with G a simple, real, non-compact Lie algebra such that G tends to C is not simple. That's what I claim is an equivalent description of what all the pairs of this type look like. Because remember, there's one identity that if I take a Lie algebra, I complexify, then I regard it as a real Lie algebra. Let's see. Pardon?
Do I need to ask that the complexification is not simple? Because if this guy is simple, G is simple.
Correct. So for this pair here, for the dual pair, G is not simple. Right? Under our duality, so if I had a GK was dual to G prime K, then by definition G tensor C is isomorphic to G prime tensor C, because G prime was just this real subspace inside G tensor C. So if I complexify G prime, I get the same thing. On a duality, complexification is the same. For this first type, for the compact type, of course, its complexification is not simple. It's the sum of two simple things. So therefore, the same thing must be on the right-hand side. This here must be GK must be a Lie algebra G whose complexification is not simple. But as real Lie algebra, it's simple. So it's simple as a real Lie algebra, but when I complexify, it's not simple anymore. And so another way to describe this. So I think this is okay, so let me just describe it like this. So I'm not going to need it in more detail. Type 3 is G comma K. I think I have the numbering off, but let me finish it, then I change the numbering. G comma K with G compact simple. And this I claim is then under duality due to something of type 4. I'm going to write down the correct types a little bit later. The dual to a pair G prime H, K, where G prime is non-compact, simple, plus the classification is also simple. So that's how I differentiate the two types. This here is a pair, G comma K, where the classification, where G is simple, but the complexity is not simple. And here it's one where G is simple, non-compact, but the classification is simple. Of course, which then means that when I go to the dual pair, since they have the same classification, that's also simple. So these two here are the compact ones. These two types, and here are the non-compact ones. So compacts are two types, right? G is not simple, then it's just the Lie group itself. G is simple, then that's a large class of symmetric spaces. These are all non-compact. Again, they fall into these categories of classification, simple or not. But there's a duality. Let me see what the real numbering is. This is actually called type 1 compact simple. What's this called? This is called type 2. It's not important, but that's what Catan, that's what everyone else calls it. G tensor C simple is type 3. And it's called type 4. Because it's much easier to remember what they are and then what the type is called. So when I classify, all I have to classify is type 1. That's all I have to do, I claim. Because of duality, right? If I classify compact, I classify non-compact because of duality. And this is classification of compact simple Lie groups, which we think we understand. And therefore, this, all that's left is this. So how do I classify type 1? Let's do just some simple examples. So G is compact simple, so we know what they look like. So we have a list of the possible groups G. So G was SON or SUN or SPN, or the exceptional ones. So those are the possibilities for G for all symmetric space of type 1. And now do the classification case by case. Let's do, as an example, SON maybe. That's probably the simplest one. So what symmetric space exists there which are quotients of SON? That means I have to have an involution, right? So I have to, that's called the Lie algebra, just Q-symmetric matrices. I have to find an automorphism of this Lie algebra. Which is an involution. So for this, I have to recall some facts about automorphisms. So there's a proposition we did prove, which said that if G is semi-simple, then out G, what in G was finite. was a property of, or in other words, in G was the identity component of out G. This was another way of stating that. This is a finite group.
We don't need compact.
No, you don't need compact. Because you can actually reduce it to the compact case by observing that if I complexify, I get the same group of automorphisms. Then I can take a compact real form, and I get again the same group of automorphisms. So I can reduce it to the compact case if you want. So that's not the issue. And then there's another thing which we didn't do, and this is isomorphic to the symmetries of the Drinking diagram. If you know what the Drinking diagram is. So for example, what if I have say SUN? This was a Drinking diagram of SUN. Symmetry means it takes dot to dot, right? Preserves connections, only one. So out here, out mod int must be Z2. And for SUN, we knew an automorphism, namely A goes to A bar. That's an automorphism. And we discussed that it's outer, so it must generate Z2. So it means I know all automorphisms of SUN. There is a conjugation, excuse me, there is a conjugation of the inner ones, or it's a complex conjugation. That's it. For SON, it's a little more interesting. So I play out SON, not int SON. Is one of the following three. It's trivial if n is odd. It's Z2 if n is even and not equal to 8. And it's a symmetric group on 3 letters if n is equal to 8. So the second trivial or Z2, except for this very special case for SO8, where you have an order 3 automorphism. That's what this means, right? There's still a Z2 in here. In involution, it's at S3. In addition to involution, you need something of order 3 to generate the symmetric group of 3 letters. And this is because the Drinker diagram looks like this. And there's a symmetry that rotates it. It's a degree 3 automorphism. I'm not going to discuss that, but actually we're going to see it's not important. What is Z2? I claim Z2 is generated by something we saw.
What's it?
The Z, the out mod int for SON is Z2, and I want to generate of that Z2.
The conjugation by -1.
Right. So, correct. So this is conjugation by the matrix G, which was -1, 1, 1. Something in ON and not in SON. So for SOT, so for in SO2N, for the even case. In the odd case, that's still inner. Okay, so let's use that information now. But of course, notice that this element sits inside O2N. Right, so I could say that out SON mod int SON is actually equal to out to int or the equal of ON, which takes G into at G. Right, it becomes on the full D algebra because that certainly lies in O2N. So I can represent, now the legal level, of course, it becomes conjugation. So what do we have to do? So G is SO2N. legal G is SO2n. Well, actually, two n plus 1 would be easier because it's there's nothing outer. First, observe that our involution, so I need a sigma, which is an involution, right? Automorphism, which is an involution. And I claim if sigma and sigma prime are conjugate, so in other words, sigma prime is equal to, or even for an automorphism, doesn't have to be conjugate. So if sigma prime is A composed with sigma, composed with A inverse, where A is an automorphism of G, this is a general statement actually, then sigma and sigma prime define the same symmetric pair. Maybe so G sigma and G sigma prime would then be two symmetric pairs, but the automorphism A conjugates one to the other, so it takes G sigma to G sigma prime via A. And of course G to G. So I get an isomorphism in two symmetric pairs. So I have to classify these automorphisms only up to conjugacy, or only up to outer or inner automorphisms, but we know in the case of the orthogon group, they are all conjugations to something in On. Okay, so let's first say sigma is conjugation by G. G is an element in On. And I can actually assume it's an SON because everything is inner. Although we can do the same thing for the other one. So if I want to change sigma into a new sigma prime with an automorphism, A is again inner, because every automorphism is inner. So I can choose, say, a C sigma prime and change sigma to A sigma A inverse. So that's conjugation by G prime, conjugation by G, conjugation by G prime inverse. And of course, that's conjugation by G prime, G prime inverse. So in other words, the involutions I have to look at, represented by some element G, I can choose an element of the conjugate class of G that is easier. So stated. If G and G prime are conjugate, then sigma is equal to CG, and sigma is equal to CG prime to find the same symmetric space. Because I have to now bring G into normal form. Right? There are nice normal forms for such things. G is an element of the orthogon group. But of course, I have one more condition. I need this to be an involution. Right? I have to have automorphisms which are an involution. So what is it? This is conjugation by G squared. This must be the identity. What does that mean? G squared lies in the center. And we're doing the odd case, so a center of SO2n plus 1. But that's trivial. The odd case there's no center, which means G squared must be the identity. So what's the normal form of a matrix whose square is the identity? And is orthogonal? Plus and minus 1 along the diagonal. So in that case, what's the fixed point set? So SO 2n plus 1 fixed under this conjugation by this element. We've seen that before, right? That's Grassmannian. So SO 2n plus 1 sigma is SOK cross SO S2n plus 1 minus K. We have K plus signs or minus signs here, right? So Grassmannian. That's all that can happen for the orthogonal group, for the autoorthogonal group.
Why do you know that the automorphism A is an
Because of this. This is something you have to assume, right? So from this theorem that I said it's the same as the symmetry of the Dynkin diagram, you have to accept then. You have to know the Dynkin diagram, observe there are no symmetries. Okay. So that's a non-trivial fact. So this description of what these good things look like, we're going to accept and use it. Okay. So that's it. There's only one quotient for SO2n plus 1, which is symmetric. That's very easy. Let's do the next example, which is SO2n. So then this is Z2, but the only complication is it's still conjugation, but the element G could be something like this. Okay. So we can still say, well, our involution is conjugation by G, but now G lies in O2n. Okay. And again, I can conjugate with something else, just like I did over there, and say, well, if I conjugate the element G with something, then the old automorphism, new automorphism give me the same thing. So I only need G up to conjugacy. So otherwise I get the same symmetric pair. So I will continue as before, right? Sigma squares the entity. That's CG squared, which means G lies in the center of O2n. But now that's plus or minus identity. G squared, yes. So what are the possibilities? Let's say G squared is plus identity. Then it continues before. Right? Then I'm in this case here. Up to conjugacy it looks like this. And the fixed point set is the Grassmannian. So in this case here, I get the Grassmannian. SO2n divided by SOK. SO2n minus K. That's my symmetric space. So the only new case is G squared is minus identity. So what's the normal form of an orthogonal matrix whose square is minus identity? It's like a compact structure, right? On R2n. So n must be even. Well, we know n is even, right? Like a compact structure, so orthogonal compact structure. So it's a normal form. Right. So up to conjugacy. So now I have to, so that's my automorphism is now adjoined by this sigma. Let's think of this as a compact structure. So what's the fixed point set of SO2n under this automorphism sigma? Sigma is conjugation by G. So it's conjugation by a complex structure. So let's write it out maybe. That's a set of all elements in SO2n such that A, J inverse is A. That's unitary group, complex linear. So that's equal to UN. identity inside SO2n. And that was another symmetric space that we saw earlier. So the only equation. So what's the conclusion now? If I take the orthogon group, what quotients are symmetric? There are actually only two of them if you want to. One is a Grassmannian. In all cases, only Grassmannian, even case Grassmannian, plus SO2 module, and that's it. So we're done with the classification for that simple Lie group.
Only one question. It's the same problem in the list because the conjugation by G squared is identity, but it's on SO2n. And you play that G squared needs to lie in the center of O2n.
Yes. So in here G was allowed to be in O2n so that this includes also the outer homomorphism. But this will be inner when G is in SO2n and outer when G is in O2n. So here I'm including all possible outer morphisms of the Lie algebra. Okay. And then see G squared must be identity, but see. Correct. So maybe I should conjugation by G squared restricted to SO2n is identity. So does this imply that G squared is plus minus identity? That's still true, a claim. Because you're right, so we're not a priori saying that conjugation with G squared is identity on all of O2n, it's on SO2n. You're right, so it's a little bit careful, but nevertheless, I think this is okay.
When you fix this with maximal torus argument, you used it was a maximal
Well, the maximal torus theorem only applies to connected Lie groups. So O2n, if I want to work in O2n, it's not connected, so we will be careful. But of course, nevertheless, every orthogonal matrix is conjugate to something, has a normal form, which actually does lie in the maximal torus. Except there might be a -1 at the end, so it's a 2 by 2 blocks, 2 by 2 blocks, and the last one could be a plus or -1. So every matrix is conjugate to something like that. So that's probably how we should argue, right? So we should say that G is conjugate to a matrix of the type 0, A1 minus A1, 0, and so on. And now what's the square? Square is minus A1 squared minus A2 squared, and so on. But conjugation by G squared, so this must commute with everything in the special orthogon group. Let's see. What am I saying?
It's okay because G lies in O2n.
Yes?
G squared in any case lies in SO.
Okay.
So it's okay.
Saved by the bell. Because this was a normal form in the Lie algebra, not in the Lie group, so I have to argue differently. Thank you. So G squared is around SO2n. That's certainly a simple way to solve that problem. Okay.
Kind of the same question as before. Now the classification is up to conjugacy and up to complex conjugations.
What do you mean by complex? Up to conjugation. Conjugation possibly by an element in O2n.
You raised that the outer automorphisms in the inner case were not trivial.
Correct.
It's two minus each other.
And they were given by conjugation with something that lies in the other component. That's what the automorphism looked like when the group is Z2. Right? I'm using that fact now, right? That I can write it like this, where G lies in O2N. That includes both in and outer ones. And that simplifies the argument. Okay.
So all inner ones relate.
The inner ones would be conjugation by element G that lies in SO2N. Those are the inner ones. And the only other one is conjugation by something in the other component. So it's still conjugation as far as practical computations are concerned. But then I restrict it to SO2N because I want to look at it as an automorphism on the special orthogonal group. Okay. Well, so there's one more group, the SO8, where the automorphism over S3. But notice that luckily the thing is order 3, and our automorphism must have order 2 to define a symmetric space. So the special outer automorphism that exists in SO8, I can forget about it. And the only element 2 inside this automorphism group is the same thing as this one here. So it even applies to n equal to 8, where you might think it's more complicated, because the automorphism group is so special. For the other one, let me just write down the result. SPN is actually the same kind of argument. So here the quotients I get is a Tasmanian. It's kind of the first case as before, and then I also get SPN mod UN as another symmetric space. For SUN, I have again the Gaussian. That's one possibility. And the other one is SU2N mod SO. Sorry, SUN mod SPN. Remember, SPN sits inside SU2N. And in fact, when we talked about the symmetry space, this was a complete list. And now we have proof that there isn't anything else when G is classical. This one is the trickiest one. This one here is not so bad. This is one of the Lie groups where there are no outer automorphism. Everything's inner. Inner is just conjugation. And I go through the same kind of arguments before. And I get two cases. That's not so easy. This is more interesting because I have this involution, which is conjugation. In fact, in this case, I have to consider two cases, either conjugation, where G lies in SU2N. And the other case, one has to be careful, I have to consider conjugation composed with A, where A of some matrix B is a conjugate, which is a unique outer automorphism of the Lie group. So if it's A itself, that would be easy. Then I get, I forgot one. SUN mod SUN. Where the automorphism is conjugation, its fixed percent is SUN. This was another symmetric space. I actually have three quotients for the unitary group. So you might think in this case, well, all I have to do is this one, and now the fixed percent is SUN, and that's it. Well, but a priori, you have to have a composition of this outer automorphism with something inner, and look at involutions and classify those. That's a little bit trickier. Maybe I assign that as one of the problems for one of the problem sessions. By the way, this Friday I don't want to do a problem session because tomorrow's a holiday, but next Friday I'll do another problem session. Okay, that's a classification of symmetric spaces. Let's maybe now talk a little bit about what else we can do the last.
Sir, what was the Jenkins diagram of this?
That's it.
Because the complexification of SUN
is SLNC. in this diagram of SL and C. Okay. Okay. Other topics we can cover. Well, there's a little bit more general theory we could do. One is the rank of a symmetric space. So what's the rank? For this I do, so this is an analog of the rank of the Lie group, but now I do the following modification. So I have my symmetric pair, I have my Cartan decomposition, and of course up K takes P to P. And then I look at subalgebras A inside P, which are maximal abelian. So instead of looking at subalgebras of the Lie group G, like we did earlier, which are maximal abelian, I only look at the ones that are contained in my complement, in my -1 eigenspace of isomorphism. Then one proves the following theorem. Which is very similar to what we did for compact Lie groups. If A and A prime are maximal abelian, then there exists an element in the root K such that conjugation takes A to A prime. So max abelians are unique up to conjugacy. And then, what was B? They certainly exist. I guess that's all I want to say now. So this is the analog of the maximal torus theorem, and now I can define the rank of the symmetric space as a dimension of this maximal abelian subalgebra. Okay. So I can order or distinguish symmetric space by their rank. One can describe this also that if I look at the exponential image of this A, this is a totally geodesic flat torus in the symmetric metric. Right? So kind of makes sense, right? It's a abelian. Remember, the curve is given by triple Lie brackets. So if I take something in A, Lie brackets are 0. So that makes sense that the image will be flat. It's also totally geodesic. That requires an argument. So one can also define the rank as the largest dimension of a flat totally geodesic torus inside the symmetric space.
And it's preserved under duality.
Pardon?
The rank is preserved under duality.
The duality? That's correct. In fact, the isotropic representation is essentially the same, right? I took K plus P, and the dual was K plus IP. If I see how K acts on P, it acts on IP just multiplying by I. It's the same isotropic representation. So, of course, the maximum abelian in P and IP is also the same thing. And then this here says also that they're unique up to conjugacy. So duality preserves that, the rank. Okay. Now the proposition is that if the rank of D mod K is equal to 1, so first possible case, right? What if there's nothing that's two-dimensional? What if one-dimensional is a maximum abelian one? Then one can show it's isometric to, so you simply connect it to Sn, Cpn, Hpn, or this something called a K plane, or their dual. But this here will be a hyperbolic space. No dual, that's spheres of hyperbolic space. So projective spaces and their dual are the only symmetric space of rank 1. It's an important classification. Unfortunately, the only proof that I know of this result here is by classification. So we saw the classification when G is classical. When G is exceptional, it gets more complicated. Then you have to know something about exceptional Lie groups. And then you look at the list. You compute their rank. And you see, well, these are the only ones of rank 1. Somewhat unfortunate that there's no conceptual direct proof for that. Okay, so that's maybe one topic. One can build more theory of symmetric spaces. Topic 2 we can cover is Hermitian symmetric spaces. So in terms of our description, G is K plus P. It will be a complex structure on P which commutes with at K. So that at K composed with J is J composed with at K. So in other words, at K is complex linear. That's called a Hermitian symmetric space. That has strong consequence. For example, J is integrable. The metric is scalar. G mod K is diffeomorphic to Rn. Even without assuming that G mod K is simply connected, so Hermitian symmetric spaces are automatically simply connected. They're diffeomorphic to Rn. And another way of saying something is Hermitian, but equivalent way of saying that is that K is not semi-simple. G is semi-simple, right? That's part of our setup if it's an irreducible symmetric space, but K may not be. So think of the example SO2n mod UN. It's not a simple Lie group, it has a center. Right? Or think of the example of SPN mod UN. So these are Hermitian symmetric. Particularly the Cayley manifolds, very basic examples of Cayley manifolds. And so you can recognize, if you look at a symmetric space, I can recognize right away, just looking at the pair, which one is Hermitian symmetric, which one is not. Just by saying that the subgroup must have some kind of center. So that's one possible topic we can go through. In the book, my notes have another chapter called Symmetric Space of Non-Compact Type. They have lots of special properties which are interesting. For example, so G comma K, say it's effective, non-compact type. Then again, G mod K is diffeomorphic to Rn. Particularly has to be simply connected. So the group G is then diffeomorphic to K cross Rn. K is a maximum compact subgroup. One can then turn that around, and that's often an important application. Take a semi-simple non-compact group, look at a maximum compact subgroup, then the quotient is a symmetric pair. So these are important properties of non-compact semi-simple Lie groups. There's a natural symmetric pair associated to them by looking at the maximum compact subgroup. Another property is the center of G must be trivial. And there are many other properties. So in a way, the geometry of symmetries of non-compact type is simpler. You can say a lot more about it than the ones of compact type. Although classifying them is easier for the compact type. So each one has its own advantages. Another possible topic These are what are called quaternic symmetric spaces. If you went to the seminar talk yesterday, you heard those words. The speaker was talking about quaternic symmetric spaces. So in a way, what this means is that you have three complex structures on the manifold locally. On P, and therefore on M, as opposed to only one. And there's a whole theory associated to that. And typical example is SPn plus 1 mod SPn SP1. That's one of the most important examples, sometimes quaternic symmetric. And other examples are Grassmannian. That's quaternic symmetric, and another is the complex Grassmannian. That's also quaternic symmetric. And there's a beautiful theory associated to that, which is kind of analogous to Hermitian symmetric spaces. This I don't have the notes yet. Another topic is topology of symmetric spaces. They have all kinds of special properties. Maybe write down one of which is kind of nice. There's a nice way to compute the de Rham cohomology of a symmetric space, G mod K, in a very algebraic way. I claim as an algebra, this is isomorphic to the following. Look at the Cartan decomposition, let P be the complement. Look at the forms on this vector space, just the exterior algebra. And now look at those things that are invariant under the adjoint representation of the group K. So it's like a point-wise description, algebraic description of the whole de Rham cohomology looks like. Just look at the tangent space at a point, look at forms at that tangent space, see how K acts on it, look at fixed vectors of that. This becomes a problem representation theory, if you want to. K acts on P, that's a certain representation. They're well understood. That induces a representation of lambda P. Now decompose that into irreducibles, and how many times does the identity occur? When it does, that's a cohomology group. Cohomology class, a de Rham cohomology class. Okay. So they have very nice descriptions of de Rham cohomology of the symmetric space. And then maybe the fifth topic that we can also do is holonomic groups. Where we go through the list of, so we discussed this last time, that it's either symmetric space, or it's a transit on the sphere. Back transit on the sphere, there was a long list of examples. Each one has a special geometry associated to that, and we could go through that list, talk about that in more detail, some other geometries. 5 possible topics of things we can do. I don't know if anyone right now has an opinion of what you would prefer, or maybe suggest something else.
For me, could be Hermitian symmetric or topology or one.
Do we have 3 weeks left or 2 weeks? I think 3, right? 3 weeks. So we can probably do 2 or 3 topics for those.
I wanted to see more on
Holonomy? Okay. It's important to know also, because this occurs all over the place, particularly all these geometries that are associated with holonomy. I think that would probably be a good idea, since it has connection with so many other things. Should I start with holonomy groups next week then? Discuss it among each other, right? If you want to pick something out, write me an email. Maybe unless you want to do something else, I'll start with holonomy groups next week then. Okay? Okay.